Hello everybody, welcome back to another video, and in this video we'll be looking at the integral of 1 over the square root of x minus x squared, and this is taken from one of the MIT Integration Bee Qualifier exams. So this is a pretty interesting and fun question to work on, as it requires you to do an unusual substitution, you could say. So what we'll be doing is we'll be firstly noticing that we have something minus x squared, and that something happens to be an x. So let's try using a trig sub, and we will eventually have to use a trig sub in this video, but the key is to find out what we substitute. So let's say we set x to be sine theta. Then okay, our dx is cosine theta d theta. Then we have the integral of 1 over the square root of sine theta minus sine squared theta, and then we have a cosine theta d theta. And does this help us at all? Because we have a sine theta minus sine squared theta. Well, if we try factoring out the sine theta, we get 1 minus sine theta. And there's no squared there to help us out. So what do? We see that this substitution does not work. So why don't we try setting this to a higher power of sine? Because what we notice is that if we set x to be, for instance, some sine squared theta in an ideal world, then if you substitute sine squared theta here, you get sine squared theta minus sine squared theta, and we will be able to do some nice stuff there. So let's try this. So take dx, well, we will need to use two levels of the chain rule here. So we see that we have sine squared, so we apply the regular power rule, so we bring the power down, subtract 1 from the power, but because sine theta is a function of x, then we need to multiply by the derivative of sine theta, which is cosine sine theta with respect to x, which is cosine theta, but we know that theta is a function of x, so you have to multiply by d theta. So this is our dx, and you may recognize that this is indeed the double angle identity for sine. However, this does not help us here. So let's bring our integral to the theta world. So this is equal to the integral of 1 over the square root of, and our x is sine squared theta. This is a very interesting substitution. Minus, and then x squared. So we have sine squared theta, and that is being squared. And our dx is 2 sine theta cosine theta. So let's just quickly bring that 2 multiple out and not erase everything. So we have a 2, and then our dx is sine theta cosine theta. So let's just put that on the numerator. So sine theta cosine theta, and our d theta is here. So what can we do here? So first of all, let's simplify the denominator a bit. So we have 2 times the integral of sine theta cosine theta over the square root of sine squared theta minus, and then sine squared squared, well, we multiply the powers. 2 times 2 is 4, obviously, so we have sine to the power of 4 theta. And this seems a lot more difficult, because how do you deal with that sine to the power of 4? But I'll tell you that this is actually not so bad, because let's try factoring out a sine squared. We see that we have a sine squared here, and we have an even power of sine here, so we can factor out a sine squared. So we have now 2 times the integral of sine theta cosine theta over the square root of sine squared theta. Okay, so now let's figure out what goes in the brackets. Well, we have 1 sine squared there, so that's 1. Then we minus, and what is left with the sine to the power 4? Well, sine to the power 4 divided by sine squared, that is sine squared theta, of course. And what we notice here is that we can do some even more simplification, because we do get our desired 1 minus sine squared theta. So we know that we can simplify that to, so here we have sine theta cosine theta over the square root of sine squared theta. And then 1 minus sine squared theta is, yes, of course, cosine squared theta. That comes from our famous identity sine squared theta plus cosine squared theta is equal to 1, which you can prove using a right triangle and looking at the patterns with the squares of the sines and cosines. Anyways, and here what we notice is that we have a product of 2 functions, and we have both of them that are being squared. So we can look at this as being sine squared cosine squared to the 1/2. Then we can distribute the 1/2 to each term. We see that distributing a 1/2 term or a square root will just cancel these squares from each term inside. That is so cool. So what we have here is 2 times the integral of sine theta cosine theta over, and then what is this? This is just also sine theta cosine theta. So this is really cool. We have simplified the integral a lot, because our favorite part of this video can cancel and cancel. This can be completely cancelled. We have the exact same thing on the numerator and denominator. So we're just integrating 1 in the theta world, which is of course 2 theta. However, we still need to get back to the x world. And how do we get back to the x world? Well, let's look at our original substitution. X is sine squared theta. So how do we isolate sine theta? Well, we take the square root on both sides, and we see that here sine theta is the square root of x. And we right now have in our expression 2 theta. So we need to solve for theta. So how do we solve for theta? Well, of course, we take the arc sine on both sides, because we know that the arc sine of the sine of theta will cancel out very nicely. And we see that theta is just equal to the arc sine of the square root of x. So what we have is our final answer, the integral of 1 over the square root of x minus x squared dx. That is equal to 2. Our theta now is the inverse sine, so I'll write this as the inverse sine of the square root of x, and we can put a plus c because we are done. So this is our answer, and this indeed was the answer that was on the qualifier answer sheet. So if you got this, then you would be correct. So that was an interesting trig substitution video, and thank you for watching.